Welcome back to ECE 340. What I am doing now is actually re-recording at least the first part of a lecture that was not very clean with the audio, and I want to try to make it a little bit better in this go around. Unfortunately, this time I don't have the benefit of an audience that's interested in asking questions, but hopefully we'll still be able to make this a useful lecture, or at least the first part, and we can probably do better than without much audio, which is what was happening in the last time. What I want to do today, I won't worry about the announcements and I'll move right into the goals. What I would like to do is continue or basically refresh what we'd talked about relative to the low pass filter. And once we've talked about the low pass filter, we will begin looking at the discrete time approximation and then going into a MATLAB simulation. And I don't know that we'll get much further than that in this material that we're talking about now. But where we are headed is, or you could actually think about getting into this material, which is more into chapter 5. And so I would like you to feel like you can actually move into discrete time processing of information, even though maybe what you're really dealing with right now is mostly continuous time development. But the ideas and concepts actually move very nicely or smoothly into the discrete time setting, and you can actually then find transfer functions in the discrete time system. You can then cross multiply, obtain difference equations of a low pass filter, and now you have a recursive way of producing a filtered signal that the original signal might have been noisy, and now you want to low pass filter that. You can also create an all delay block diagram from that difference equation representation, and that all delay block diagram is similar to what we've been sketching with all integrator block diagrams, except now we're in discrete time and we don't have integrator blocks, we have delay blocks, and those delay blocks may be more intuitive. Those are just holding for one sample period the information, and then after one sample period they put that particular value or number out at the output of that delay block. Beyond that, we will get into the intuition of filter design, and that will probably be in the next lecture, where we will discuss filter order and order selection and the different types of filters. Today we'll be talking almost exclusively about low pass filters, but you can immediately then be looking or thinking about high pass filters, band pass filters, and band reject or notch filters. All of those are pretty straightforward changes that can be made from once you understand the concepts behind a low pass filter. What we want to do then is remind ourselves about this low pass filter. And last time we were talking about designing maximally flat filters, or filters whose pass band is quite flat near the low frequency region, and those are called Butterworth filters. Let's now talk in this particular discussion about the design of a third order low pass. And the first thing that we do when we're designing a Butterworth filter is figure out where the poles are located. Now that if it's third order, then we actually know that since 3 is odd, we will have one real pole, and it will be located in the normalized cluster of poles at -1. And the first thing that we do in designing these Butterworth filters is create a normalized transfer function. And then, depending on what kind of frequency we're after, whether we want a 10 hertz bandwidth or whether we want a low pass filter that has a bandwidth of 100 radians per second, we can frequency scale from the normalized transfer function that will have all of its poles, the normalized transfer function, on this circle of radius 1 away from the origin. With a with a third order filter, Butterworth, the key formula for figuring out where these poles are located is the formula 360 degrees divided by 2 times n. And n for a third order is obviously 3. We're now dividing 360 by 6. That's a fairly straightforward division problem, and that says that our poles are now separated by 60 degrees. Because it's odd, n, we now know that one of those poles is at -1, and the remaining poles, will simply be separated from that pole by 60 degrees. Using trigonometry, then, we can say that the real part is going to be the cosine of 60 degrees. That gives us our 1/2. And since we are retaining the stable poles, we are going to be in the left half plane. Those two complex conjugate poles will both have a real part of -1/2. Their imaginary part is going to be the sine of 60 degrees, which ends up being the square root of 3/2. And now we have the location of all three of our poles, whether we want that in a rational form or whether we want it in a decimal form. Now we know what we're dealing with in terms of our three normalized pole locations for a third order Butterworth filter. In the normalized case, we know that our bandwidth is 1 radian per second. We can now create the transfer function for low-pass filters. We have all of our action really in the denominator. The numerator is simply a constant, and we can now put all of these factors together. We have an s+1 factor, that's our real pole, and then we have our two complex conjugate pole pairs, and putting that into the form that I like to write it in, we have s+1/2 quantity squared plus the imaginary part squared, which is the square root of 3/2. You square 1/2 to get 1/4. You square the square root of 3/2 to get 3/4. That ends up giving you a constant of 1. Then we need to figure out what's the coefficient on the s variable in s squared plus something s, and we just take 2 of the real part, so 2 times 1/2 gives us 1, and that quadratic factor then becomes s squared plus s plus 1. If we multiply that all out, we will get a third order denominator polynomial, which is what we should expect with a n equal 3, and we have then for a Butterworth pattern of poles for a low-pass filter, the denominator polynomial will have s cubed plus 2s squared plus 2s plus 1. That's now a normalized filter with a bandwidth of 1 radian per second. Now, we usually are not going to be always living with a bandwidth of 1 radian per second. We need to be able to create filters of any bandwidth that we might want, and that involves frequency scaling. And as we talked about last time, in order to frequency scale, what we do is in this normalized transfer function, we simply replace s everywhere with this new expression s over the frequency that we're wanting to create as a bandwidth. In this case, it's 10. So let's say that we want now a bandwidth of 10 radians per second. Everywhere in the normalized transfer function, which was this h of s equal to 1 over s cubed plus 2s squared plus 2s plus 1, everywhere we see an s, we replace it with s over 10. Doing that now produces a third order low pass filter with a bandwidth of 10 radians per second. We could keep it in what I've labeled here, or what I've drawn here as h sub 1 of s in black, but that now in the denominator gives us s cubed over 1,000 plus 2s squared over 100 plus 2s over 10 plus 1. That's a little bit ugly. We could, I guess, put the 1,000, the 100, and the 10 upstairs by saying 0.001 in the scaling of s cubed. But we can clean that up if we simply multiply by 1, where 1 now is written as 1,000 over 1,000. That now eliminates or gets rid of that 1,000 in the leading coefficient of this low-pass third-order filter, and we now are left with, in terms of a transfer function, capital H sub 1 of s is now 1,000. That's coming from the 10 cubed upstairs, and we now have the 1,000 scaling all of the terms in the denominator. We end up with a monic denominator polynomial, or a monic meaning that the leading coefficient has been normalized to a value of 1. That's the monic. The other terms now just get scaled by 1,000 divided by the appropriate factor in the denominator. In the s squared term, we had 2 over 100, which we now scale by 1,000. That gives us 20. In the linear term, or the s to the 1 power, we have 2 over 10, which we scale by 1,000. We have 2 times 100, or 200, and then we scale the constant 1 by 1,000. We now have this third order low pass filter with a bandwidth of 10 radians per second for our design. And that wasn't that hard to do. We simply had to figure out how our poles were separated based on the order of the filter. We create this normalized filter. We frequency scale that filter, and now we have our low pass filter that we can play with or use in many different ways. Now, you might say, could we go ahead and look at that in MATLAB just to check our work? And yes, we can. We can go into MATLAB and we could say, what did we actually have? We have several different ways of looking at this. We could say, let's just sketch the Bode plot of our resulting filter, and we had then a numerator of 1,000. We had a denominator, d1, which was cubic. We had s cubed plus 20s squared plus 200s plus 1,000. That's now the denominator of our low-pass filter. We can now create this object, let's just call it filter 1, as a transfer function as the numerator polynomial and the denominator polynomial. This now should be our third order low-pass Butterworth pattern filter. And if we were interested in, which is what we said we wanted to look at, is the frequency response of that filter, we can now just say Bode filter 1, and MATLAB will hopefully conveniently give us that Bode plot that we asked for, or that we were expecting. And you can see then that the passband is very, very flat. It's 0 dB, which means that an input in is going to be unscaled in amplitude as it comes out. We have the bandwidth of 10, and we can see that at 10 radians per second, we're down about 3 dB. We will be down at 3 dB. Our phase is now, because it's third order, it's going to be 3 times this minus 45 degrees. And eventually, for high frequencies, because of the third order behavior, our phase is now all the way at minus 270, and we're rolling off into the stop band at a slope in the magnitude response of minus 20 times 3, or 60 dB per decade. And you can see that if you go out and look at the two different decade or this decade expanse in frequency and indicate that you're now going from, let's say, minus 60 dB at 100, and then by 1,000 you're down to minus 120 dB, which is the 60 dB per decade. We could play a little bit more with this, or we could just look at, let's say somebody says, well, I really want to see if those poles are where I think they should be. We could simply do the pole of that transfer function, filt1, and let's just call those poles P1. And actually they are now at where we thought they should be. They're at minus 10, and then we have two complex conjugate poles at minus 5 plus and minus J 8.66. If we weren't real comfortable with that, we could say, well, what's the magnitude of those poles at P1? And we could say the absolute of P1. And now we can see that indeed those complex and real pole values have a magnitude or a distance away from the origin of 10. And that's giving us now something that we can sort of feel good about. If we wanted to build up that filter a little bit differently, suppose that we said, oh, I like to play with the normalized filter to begin with. That normalized filter, the normalized meaning we had a bandwidth of 1 radian per second, it had then for a polynomial s cubed plus 2s squared plus 2s plus 1. And we could say, well, what are the roots of the normalized, or where are the poles of that particular polynomial? And you could say, give me the roots of d1 normalized, where we're saying roots is trying to find the roots of a given polynomial. And now those are the pole locations that we would have expected. We could now, once we have those poles, we could find our denormalized or frequency scaled poles by simply multiplying those normalized poles by whatever scaling factor we wanted. In this case, we wanted to put them at 10, so if we multiply P1 norm by 10, we should end up with the poles where we want those, and now we could actually build up a polynomial from that, and we could say our D1 denominator 1 polynomial that we're checking is going to be the polynomial poly created from the poles from P1 check. And that now is consistent with what we had before, and so now we have this other way of producing this transfer function that has a bandwidth of 10 radians per second. We can do it immediately, or we could build it up from the normalized set of poles and the numerator expression. Let's now go back to our lecture and start building up a differential equation associated with this third order low pass Butterworth filter. And what we want to actually do is create a state space representation of this system, and then we will actually be able to manipulate that state space or discretize that state space. What we want to do then is first take this transfer function and go into a differential equation form. Once we have the differential equation form, we want to now put that into a block diagram, and I want to actually, in this portion, create a block diagram that's a little different than what I've created in the past, or create it differently than what I've created it in the past. To create the differential equation, if we cross multiply, and that means then we take that s cubed denominator and multiply that by the Laplace transform of the output, capital Y of s. We take the numerator, 10 cubed, and we're now multiplying that by the capital X of s, which is the Laplace transform of the input. We simply have to remember the relationship between multiplication by s in the frequency domain corresponding to differentiation in the time domain. And now if we have an s cubed times y, capital Y of s, that translates into y triple prime, or the third derivative of y with respect to t. Then we have plus 20s cubed, which in the time domain gives us 20y double prime, plus 200y prime plus 10 cubed y of t is equal to 1,000 x of t. Now what we want to do, now that we have the differential equation, somebody could say, okay, that's the differential equation that governs the dynamic behavior of a third order low pass filter that has Butterworth poles as its characteristics. Now what I want to do is create an all-integrator block diagram, and as I said before, I want to build this up a little differently than what we've done in the past. But what I will assume is I'm going to assume off the bat that I have available to me to measure the input x of t and the output y of t. And from that information, I'm now going to be able to build up the entire block diagram, and you should expect 3 integrators. Since this is now a third order differential equation, our block diagram should end up with 3 integrators that are interconnected in such a way that if we injected the input signal x of t into the input of that block diagram, out will come the output y of t that satisfies this governing differential equation. Now, the block diagram that I want to build, the way I want to build it is actually to initially take this entire differential equation and pull all of the terms to one side of the equality. Meaning, let's now start with y triple prime of t plus 20y double prime of t plus 200 y prime of t plus 1,000 y of t minus 1,000 x of t, and let's let that equal to 0. That's now our starting form for this block diagram construction. And again, what I'm assuming I have available to me is the input x and the output y. To build up the block diagram, the first thing that I want to realize, and I'm going to have a lot of different variables floating around, so let me just create one that I'm going to call alpha, and I'll start with alpha. That's now equal to all of these combinations of derivatives of y and the input x. Now that I have alpha as that expression, let me create or start to create or build this block diagram and say the very first thing that I'm going to do is I'm going to inject into this block diagram a signal alpha. That signal alpha is equal to what? It's actually just equal to 0. And in that sense, I really don't even have to include that alpha signal at that location. So as eventually, I will be able to simply remove that signal, and I haven't changed my block diagram at all because alpha is just 0. Now, what I said is I said, let me assume that I have the input x of t available to use. Let's say that is right here. And let's also say that I have the output y of t available for measurement. If I have those available to me, look at what I can do to this original differential equation, all of the terms being on the left-hand side. I can actually add 1,000 x of t to that expression. I can also subtract 1,000 y of t from that left-hand side. If I put that into the block diagram, what I'm saying is I take 1,000 and I use that to scale x of t, and I add that in to, or I add that to alpha. I'm also taking y, scaling it by 1,000, changing the sign, and now putting that into that summing junction. And out of that summing junction, I will now have a new quantity, which I could call, let's just call this maybe alpha 1. Alpha 1 is going to be what's left when I take 1,000 y plus 1,000 x and add that in algebraically to alpha, which then allows me to conclude that alpha 1 is actually equal to y triple prime of t plus 20y double prime of t plus 200y prime of t. That's now what alpha 1 is. And what I want to do now is actually integrate that and produce a new signal. I can call that alpha sub 2. If I integrate alpha 1 and call that alpha 2, what I really am saying alpha 2 is equal to is the second derivative of y plus 20 times the first derivative of y plus 200 times y of t. And I hope you can see that now I can start taking the output y, scale it by 200, change the sign and add that to alpha sub 2, which now gives me a new expression, which I can call alpha sub 3. Alpha sub 3 is now going to be the second derivative of y plus 20 y prime of t. That's now what's coming out of this second summing junction. And I believe we can pick up with the second half of the lecture at this point.